The Lagrange theorem is one of the fundamental concepts in group theory. This is actually in connection to the idea of the identification of subgroups of an already identified group. This is often used because there is a good connection with the order or the cardinality of the subgroups identified in the original group. The Lagrange theorem is stated in this manner: if G is a finite group and H is a subgroup of G, okay, then the order of your subgroup H, represented by this notation, divides the order of group G, represented by this notation. So what does this tell us mathematically? Now, in notation further, it tells us this manner that the order of H divides the order of G, or in other sense, the order or cardinality of any subgroup that you could determine is actually a factor of the order of G. Now, this means that the interpretation of that is, for the identification of subgroup, your subgroup cannot just have any size or any indetermination of subgroup. There is a idea that the order of the subgroup that will be determined is actually related to, or a factor in this case, to the order of G. So, okay, it must be a divisor of the size of the whole group. Take note that order talks about cardinality. In short, say for example alone, if the order of G is actually 12, the subgroups that can be determined in this given set, whatever will be the operation, would have orders. So let's say the order of any subgroup that would be determined would be factors of 12. 1, 2, 3, 4, 6, and then 12. In short, we cannot have any subgroup with order 5. We cannot get any order subgroup of order 7 or order 10. It would be subgroups of order either 1, 2, 3, 4, 6, and 12. Take note that 12 corresponds to the improper subset, the G itself, and your 1 corresponds to the set containing your element, identity element. Okay? So this is in connection with the identification of subgroups. So we will be guided, okay, with the possibility of the order or the sizes or the cardinality of our subgroups. But take note, there are also some things that we need to understand here, or cautions. This is only for finite group. Okay, so if G is a finite group, meaning the number of elements there can be identified, limited rather. Okay, so because if for infinite groups, the order doesn't necessarily matter, because say for example, if the finite group is, if G is actually infinite, then its order is infinity. So there is no specific number using this that can divide infinity. Okay, so there is no factors for infinity, for infinity is not necessarily identified at this point. Another thing for this is, some caution for this is, if we're going to use the Lagrange theorem, yes, it tells us that the order of your possible subgroups are factors or divisors of the order of your group, but there's no there's no, what they call this one, there's no assurance that you could always get a subgroup of this size. The assurance here is that you cannot have any subgroup of order which are non-divisors of your order of your set. It will only be, for this case, 1, 2, 3, 4, 6, 12. In short, order of 7 is no longer possible. Order of 5 is no longer possible. Order of 9, 10, 11 are no longer possible here. But it doesn't necessarily mean that you really need to come up with a subgroup of order 4, because there is some instances where even the subgroup of 4 is not possible to be determined. It's just that this is just a guide that it's possible to get a subgroup with order 4, but it's not an assurance that there is always a subgroup of order 4. Now, this Lagrange theorem is discussed because previously we talked about identifying the subgroups of a certain group. And let's try to go back to that using this idea of Lagrange theorem and determine the subgroups that we have developed or gathered, and those subgroups that were not possible if it fits the idea of Lagrange theorem, because our first example is also a finite group. Let's wait for that in the next video. Thank you very much for watching.